Hey again, everyone. We're going to start our lessons on electric circuits, starting with the idea of voltage. Uh, you have this presentation. You can follow it along with me. Uh, you can even print out your term maps to have them handy and fill things in as you go. You might even want to search for images for the term maps before you print them out, or just leave them all electronic. It's completely up to you. But some of you did ask me if it was okay to print the term maps out and upload pictures. Perfectly fine if you're more comfortable with the paper versions. Anyway, here we go with electric circuits. Please watch all of these videos before you attempt the exit tickets. I've snuck a few questions in there that you can only answer if you listen to me in the videos rather than just skipping to the questions at the end and trying to go back and find answers. Don't do that. Just do me the respect of watching the videos. I put a lot of work into the presentation in these videos. They're not that long. So here we go with electric circuits. This is the real practical use of electricity. You studied electrostatics last week. Electrostatics is really just a fundamental idea that there are forces involved with electricity and that electrons and protons carry charge. Putting them together in circuits is a way we take advantage of these physical properties for practical use, as you're doing right now by watching this video. So again, the first idea we're going to talk about is the measurement of voltage, also known as electric potential. So to discuss this, we need to go back to the idea of electric field. On the screen here, you see two metal plates. We have one up top and one down below. They are parallel to each other. We're going to make the top plate positively charged and the bottom plate negatively charged. Now, since this is the case, we're going to have an electric field between the plates. Now, you saw with the hopefully with the simulation. I know it didn't work for a lot of you. For me as well. I only have Chromebooks in the house. The electric field is always drawn away from positive charges and toward negative charges because the electric field is telling you what a positive charge would do if it were placed in that space. So in the case of our two plates, positive up top, negative down below, any charge placed in that space would want to go away from the positive towards the negative. So in this case, straight down. Well, that means if we have a positive charge that we want to go up to that positive plate, we're going to need to do work in order to accomplish that goal. To push against the natural electrostatic force requires energy. The energy that this electric particle would gain if we were to accomplish that action of pushing it up against the electric field would be equivalent to the electric potential energy it gains. This is the exact same idea as gravitational potential and gravitational potential energy. If I've got an object here, this one's Sophie, and I want to lift it, well, I have to do work to do that. There's a gravitational field always around us from the Earth pointing straight down. So if I want to take an object with mass and lift it against that field, I have to put energy into it. This is doing work. I won't bother you anymore. So here's our positive charge flying in. That required work to accomplish. We don't really talk about electric potential energy. Instead, we talk about electric potential, otherwise known as electric potential difference between that bottom plate and the top plate, for example. This is what voltage is. It's not directly energy. It is the amount of energy per coulomb that we are using to accomplish that goal of pushing an electric charge against an electric field, against something trying to push it the other way. So again, in summary, voltage is also known as potential difference. And there are other ways to describe voltage besides potential difference. One other way it's described sometimes is electromotive force. That's an old-fashioned way of describing voltage, but it is there. That's abbreviated with an EMF or the Greek letter epsilon, electromotive force. But most of the time you'll see electric potential, voltage, maybe even potential difference, electric potential difference. It's a lot of ways to describe voltage. I'll try to use the phrase voltage as much as possible, but sometimes I'll use electric potential as well. They are the same thing. So let's take a look at the equation for voltage. Again, the definition is it's the work done, the energy used per unit of charge. So the equation is, again, voltage equals work divided by charge. So abbreviated, it's a V equals W over Q. As far as the units go, the units for voltage are conveniently volts. The units for work or energy are joules, and the units for charge are coulombs. And again, the abbreviation for those three units are V for volt, J for joule, and C for coulomb. The measurement of voltage is really, I guess, my favorite unit in all of physics for the fact that both its abbreviation as far as its mathematical variable, V, matches the variable for its unit, V for volt. There's no other measurement in physics I can think of that has the same letter for both its mathematical variable and as the unit. So good on there. I don't know why we don't do that for all the variables, call mass units or, velocity velos or whatever. But at least we can't confuse the unit and variable for volts here. So let's just take a look at an example using the equation. I gave you a couple of questions in the exit ticket that you'll look at soon involving the equation itself. So let's say we want to move a proton through an electric field of 1 volt. Well, again, anytime you use an equation or solve a problem, you want to try and identify what measurements you're given. So I'm going to show you this same problem, but I'm going to color in the important information. We want to move, the question we're answering is how much energy is required to move a proton through an electric field of 1 volt. So how much energy is required? Well, let me color those things in. We have a proton. Proton has a certain amount of charge. We have 1 volt in a field, and we want to solve for energy. So looking back to the equation, a volt is energy divided by charge, or work over charge. Work and energy are the same thing. We can rearrange that equation to say work equals volts multiplied by charge. So fill in our values. 1 volt. The charge on a proton is the elementary charge. Remember that from last week's electrostatics. 1.6 times 10 to the negative 19 coulombs. Multiply together, you get 1.6 times 10 to the negative 19 volt coulombs, or joules. I use this example specifically because this amount of energy is also known as an electron volt. We will never use that unit, electron volt, but if you look to any other texts, perhaps, usually charges are given energy values in electron volts rather than joules. But we're going to use joules. That's a standard unit that we're sticking with. That brings us just about to the end of our discussion on voltage for today. There are 2 videos here of Van de Graaff generators that I wish we could play with in live. We have them in the classroom, but I'm afraid we won't get a chance to do that anytime soon. So I'll let you watch these videos with these devices. Just to tell you the simple story, the Van de Graaff generator is a metal sphere that builds up charge of and has a potential difference or a voltage of about 10,000 volts in the sphere. And yet you can see in the thumbnail on the video on the right, you are able to touch this. Enjoy the videos, and then you can take a look at exit ticket number 1. I'll see you in the next video where we'll talk about current. Take care.